At first glance, the Stirling engine appears deceptively simple, a small, unassuming machine that could easily be mistaken for a toy. Yet beneath its humble exterior lies a groundbreaking technology with the potential to redefine how we store and use energy in a renewable-powered world. While solar panels and lithium-ion batteries dominate conversations about clean energy, this 200-year-old invention has quietly re-emerged as a missing piece in the sustainability puzzle. The global transition to wind and solar energy has exposed a critical flaw. Renewable sources are intermittent, leaving grids vulnerable when the sun sets or the wind stills. Batteries, though useful for short-term storage, struggle with longevity, cost, and reliance on scarce materials like lithium and cobalt. Enter the Stirling engine, a heat-powered device that requires no combustion, emits no noise, and can run on virtually any temperature differential. Originally invented in 1816 by Scottish clergyman Robert Stirling as a safer alternative to steam engines, the technology was sidelined during the Industrial Revolution by fossil fuel-powered machines. Now, as the world seeks alternatives to carbon-intensive energy storage, engineers are revisiting Stirling's design with fresh eyes. Unlike internal combustion engines, which rely on controlled explosions, the Stirling engine operates through a closed-cycle process where gas, typically hydrogen, helium, or air, expands and contracts between hot and cold chambers. This motion drives pistons, generating mechanical energy without direct emissions or the need for fuel. The elegance of the system lies in its versatility. It can harness heat from sunlight, industrial waste, geothermal sources, or even a simple candle flame. In Sweden, a company called Ailio has unlocked the engine's full potential by pairing it with thermal energy storage (TES), a method far older than the Stirling engine itself. Their innovation involves heating aluminum blocks to 600 degrees Celsius, triggering a phase change that locks in energy with remarkable density. When electricity is needed, the stored heat activates Stirling engines to produce both power and usable heat, offering a combined 39 kilowatts per unit. This system thrives where batteries falter. It delivers consistent output regardless of weather, suffers no degradation over decades, and poses no fire risk. Beyond stationary storage, Stirling engines already demonstrate their reliability in extreme environments. Sweden's Gotland-class submarines use them for silent propulsion, allowing weeks-long submerged operations without refueling or detectable noise. In Arizona's Maricopa solar plant, arrays of mirrors focus sunlight onto Stirling receivers, achieving over 30% conversion efficiency, a figure that rivals photovoltaic cells. These real-world applications underscore a key advantage. Stirling engines are agnostic to their heat source, making them adaptable to diverse climates and infrastructures. The environmental case for Stirling test systems grows stronger when examining their life cycle impacts. Ailio's units emit just 23 grams of CO2 per kilowatt-hour, outperforming lithium-ion batteries, 32 grams per kilowatt-hour, and dwarfing diesel generators, 523 grams per kilowatt-hour. With no rare earth metals or toxic electrolytes, their components are infinitely recyclable, aligning with circular economy principles. Perhaps most compelling is their 30-year lifespan without performance decay, a stark contrast to batteries that require replacement every 10 to 15 years. This durability makes them ideal for off-grid communities and industrial settings where maintenance is challenging. Already, Stirling TS hybrids are powering Morocco's Noor Ouarzazate solar complex and Dubai's Mohammed bin Rashid Al Maktoum solar park, the latter aiming for 5 gigawatts capacity by 2030. In rural Africa, modular units provide 24/7 electricity to hospitals and schools without reliance on diesel shipments. The scalability of these systems hints at a future where energy storage isn't just electrochemical, but thermal-mechanical. As Ailio expands across Europe and Africa, their projects collectively represent 426 megawatts of capacity, enough to power 300,000 homes. The resurgence of the Stirling engine challenges a persistent myth in clean tech, that innovation must always mean invention. Sometimes, progress involves rediscovering overlooked ideas and refining them with modern materials and digital controls. In an era obsessed with high-tech solutions, this quiet machine reminds us that simplicity often holds the key to resilience. Its revival also signals a broader shift toward energy-agnostic systems that prioritize flexibility over single-source dependence. By decoupling electricity generation from storage, Stirling TES configurations allow renewables to behave like baseload power plants, a critical step toward phasing out fossil fuels entirely. The journey from teacup toy to grid-scale solution mirrors renewable energy's own trajectory, dismissed as impractical until engineering and necessity converged. What began as a 19th century curiosity now stands poised to address 21st century energy gaps, proving that sometimes the future is hidden in plain sight. The Stirling engine, a silent revolution in clean energy. Part 2. The marriage of Stirling engines and thermal storage represents more than a technical breakthrough. It reimagines the very architecture of energy systems. Traditional grids are built on a just-in-time model where supply must constantly match demand, forcing reliance on peaker plants during shortages. Stirling hybrids flip this paradigm by stockpiling energy as heat, a medium far cheaper and more stable than electrons in a battery. Aluminum's phase-change properties make it ideal for this role. At 600 degrees Celsius, it absorbs latent heat without rising further in temperature, creating a thermal bank that cools predictably when energy is withdrawn. This predictability allows operators to dispatch power precisely when needed, smoothing out the erratic output of wind and solar farms. Unlike pumped hydro or compressed air storage, which require specific geographies, Stirling TES units can deploy anywhere with minimal infrastructure. A single Ailio module fits inside a shipping container, delivering 13 kilowatts of electricity and 26 kilowatts of heat, enough to sustain a small factory or apartment block. Networked together, these modules form virtual power plants that balance grids without massive lithium installations. The economic implications are profound. While lithium-ion batteries cost $200 a kilowatt-hour and degrade, TES Stirling systems achieve EVs, E50 per kilowatt-hour over their 30-year lifespan. This price gap widens further when considering ancillary benefits like heat cogeneration, which offsets boiler use in district heating systems. For developing nations, the technology offers a leapfrog opportunity, bypassing fossil fuel dependence and unreliable battery supply chains altogether. In Malawi, off-grid clinics use Stirling TES units to refrigerate vaccines and sterilize equipment, tasks previously hampered by diesel shortages. The end-gain silence and zero emissions make them equally valuable in urban settings, where noise pollution and air quality are growing concerns. Industrial applications are equally transformative. Steel mills and cement plants, which account for 15% of global CO2 emissions, can capture waste heat often exceeding 800 degrees Celsius to power Stirling arrays. This turns a byproduct into an asset, reducing reliance on external electricity purchases. Data centers, another energy-intensive sector, are experimenting with Stirling engines to recycle server heat into backup power, a closed-loop solution that enhances sustainability. Even the agricultural sector benefits. Greenhouses use daytime solar heat to warm thermal banks, releasing energy at night to maintain optimal growing temperatures without gas heaters. The Swedish military's submarine program highlights another advantage: energy security. By running on liquid oxygen and diesel or biofuels in peacetime, Gotland-class subs achieve unprecedented stealth and endurance. This same resilience applies to civilian microgrids, where Stirling TES systems provide islanding capability during blackouts or cyber attacks. Their mechanical simplicity also makes them resistant to electromagnetic pulses, a growing concern for critical infrastructure. Critics argue that Stirling engines face efficiency limits compared to turbines, but real-world data tells a different story. At Arizona's Maricopa plant, solar Stirling systems achieve 31.25% net efficiency, outperforming many photovoltaic farms. When paired with TES, round-trip efficiency of electricity to heat to electricity reaches 60 to 70%, rivaling lithium-ion's 80 to 90%, but with far superior longevity. The gap narrows further when accounting for lithium's performance decay. After 5,000 cycles, batteries retain just 80% capacity, while Stirling engines maintain original output indefinitely. Material availability further tilts the scales. Aluminum is the Earth's most abundant metal, with established recycling streams. Lithium, cobalt, and nickel supplies, by contrast, face geopolitical risks and environmental harms from mining. TES Stirling systems also avoid the flammability issues plaguing batteries, as seen in electric vehicle and grid storage fires. The roadmap for Stirling technology points toward even greater integration. Researchers are experimenting with supercritical CO2 as a working fluid, which could boost efficiency to 50% by exploiting higher temperature differentials. Additive manufacturing now allows complex heat exchangers to be 3D printed, reducing engine size and cost. In Chile's Atacama Desert, a pilot project combines Stirling engines with saltwater thermal storage, using the ocean's temperature gradient as a free cold sink. Such innovations hint at a future where Stirling farms complement solar and wind installations globally. The psychological barrier may prove harder to overcome than technical ones. For decades, energy discussions have been dominated by photovoltaics and batteries, creating a blind spot for alternatives. Policymakers and investors must recognize that no single solution can meet all storage needs. Diversity is essential. Just as ecosystems thrive on biodiversity, grids need a mix of storage technologies: batteries for short bursts, hydrogen for seasonal storage, and Stirling TAs for daily cycling. The quiet revival of this 19th century invention carries a profound lesson. Sustainable transitions need not always rely on untested futurism. Often, the tools we need already exist. They simply await rediscovery and refinement. As climate deadlines loom, the Stirling engine's second act demonstrates that pragmatism can outshine novelty. Its journey from obscurity to necessity mirrors renewable energy's own rise from fringe to mainstream. In the end, the measure of a solution isn't its complexity, but its ability to meet human needs reliably and affordably. By that standard, the Stirling engine, paired with ancient thermal storage principles, may well become a cornerstone of the post-carbon world. Its resurgence reminds us that sometimes progress looks less like a quantum leap and more like a forgotten idea whose time has finally come.